Hi, hello, welcome to everybody. Good morning, good afternoon, good evening. So welcome to the Hypatia Colloquium organized by the Office for Science at the European Southern Observatory. This is targeted to early career scientists. So today we will have again 2 early career scientists. We have Cristobal Bordiu and Linda Lombardo. They will be introduced by our 2 wonderful chairs of today, so Julia and Ashish. So I leave the floor to Julia. Please, Julia, take the control and go ahead and have fun.
Well, thanks, Paula. Also from my side, a very warm welcome to everyone to this episode of the Hypatia Colloquium. I am very pleased to introduce our first speaker, while Ashish, an ESO student, will then take over for the second part and introduce our second speaker. So without further ado, I'd like to introduce Cristobal Bordiu, who did his PhD at the Universidad Complutense de Madrid and is now at the Istituto Nazionale di Astrofisica, also called INAF. And so he will be talking about a molecular window into the mass loss history of luminous blue variables. And so I will stop sharing my screen now. And Cristobal, please do share your screen and the floor is yours. So we're looking forward to your talk.
Thank you so much. Can you hear me?
Yes, we can hear you.
Oh, perfect. Share. Okay, can you see my screen?
We can, yes, see your screen. So go ahead.
Okay. Perfect. Hello, everyone. Before I start, I would like to thank the organizers for giving me the chance to show my work here. So in this presentation, I will talk about massive stars and in particular, luminous blue variables. And I will try to show how we can take advantage of a molecular spectroscopy to have a more comprehensive view of their mass loss history. So the key question is, can luminous blue variables form molecular envelopes? And if so, what can we learn from the study of these structures? So let's begin by introducing what is a luminous blue variable. Here you can see some evolutionary tracks for massive stars in different mass regimes. And well, you know that massive star evolution is a complex topic, so this is an oversimplification. So I don't want you to focus on the details, but instead the point I want to illustrate is that when massive stars leave the main sequence, they undergo a series of transitional stages in which they progressively lose a significant fraction of their initial mass until they explode as supernova. So a proper characterization of these transitional phases is crucial not only to understand stellar evolution, but also to measure the impact these objects have into the surrounding medium, because they eventually alter the structure and composition of the galaxy. So the luminous blue variable phase is just a brief interlude that some massive stars experiment post-main sequence that lasts for a few thousand years. Due to this brevity, the number of luminous blue variables is incredibly scarce. We have a population of roughly 60 objects in the galaxy right now. But what are the features that define the LBB class? Well, as you will see, the name is quite self-explanatory because, well, we have a HR diagram here with some luminous blue variables. And of course, they are luminous, very luminous stars. They are hot most of the time, so we call them blue. But most importantly, they are variable. They have a very specific type of spectrophotometric variability called the S-Dor cycles that produces drastic changes in the temperature that make the luminous variables to move horizontally across the HR diagram at a roughly constant volumetric luminosity. But if you look at these stars in a specific band, for instance, in the visual band, you will observe these changes of up to 2 magnitudes in timescales that vary from a few months to several years. These light curves correspond to 3 well-known luminous blue variables, which are AG-CAR, VRI-15, and HR-CAR. But perhaps the most interesting feature about luminous blue variables is their heavy mass loss. Luminous blue variables have the highest mass loss rates of all massive stars. And this mass loss has 2 components: a stationary component caused by the stellar winds that are responsible for mass loss rates of the order of 10 to the minus 5 to 10 to the minus 3 solar masses per year, and also a random component caused by violent sporadic eruptions that expel several solar masses of processed material into the surrounding medium in very short timescales. So, of course, all these processes produce the formation of large circumstellar nebulae, like the homunculus nebulae that you can see here on the left. And this is perhaps the best example of this kind of structures. The homunculus nebulae surrounds Eta Car, which is a massive binary system in which the primary is a luminous blue variable that has a mass of around 100 solar masses. And this star suffered a huge eruption in the 19th century, around the year 1840, that's called the Great Eruption. And this event formed this bipolar structure that you can see here. So the thing about LBB nebulae is that their study is crucial to understand and reconstruct the mass loss history of these objects, because we can also retrieve the chemical evolution of the parent star. And this is a fight that has been traditionally fought in two fronts. First, the infrared domain, because far-infrared emission traces the dust content of this nebulae. And here you can see some examples belonging to 6 luminous blue variables that are surrounded by shells of dust that are visible in the MIPSGAL 24 micron survey. And on the other hand, we have the radio continuum observations, especially at centimeter wavelengths, that trace the ionized gas content of the nebulae. And for comparison, here you can see the same objects, but this time seen by the Meerkat Galactic Plane Survey at 1.3 gigahertz from a paper that we are working on. And the one thing that I want you to notice is that ionized gas and dust don't always trace the same structures, the same regions of the nebula. So this underlines the need of this type of complementary observations that are kind of synergistic. And they are crucial to have a global view of the mass loss processes of these stars. But there is an obvious question here. Is there anything that we are missing, some missing piece of the puzzle that we are not observing? Or more precisely, is there molecular gas in these objects? And the answer is complicated, because probably when you think about molecular envelopes around evolved stars, you think about the typical circumstellar envelopes around AGB stars. However, these circumstellar envelopes have a well-defined schema where some molecules are formed very close to the stellar photosphere under thermodynamic equilibrium conditions. Then you have the dust condensation zone where gain chemistry dominates, and then you have a region of active photochemistry. However, this schema does not hold for LBBs because the initial conditions are very different. The temperatures are way hotter. We're speaking of effective temperatures of several tens of thousands of Kelvin. And also the strong UV fields of these stars should theoretically destroy any molecular material in very short timescales. But the fact is that some molecules have been detected in a handful of luminous blue variables thanks to millimeter and submillimeter spectroscopy. However, this poses a problem because we are not always very sure about what is the origin of these molecules. They could be just interstellar material that has been compressed by the stellar winds, or they could be molecules that form in situ from an eruption from stellar ejecta. So let me quickly review the main milestones of this line of research. The first detection of molecular gas was achieved almost 20 years ago in Eta Car with the detection of molecular hydrogen. Then a few years later, several concentric shells of carbon monoxide were detected in another luminous blue variable, G7929. This was followed by the detection of large molecular clouds around G24 and G26 that were somehow disturbed by the stellar wind of these stars, but the relation of the gas and the stars were not that clear. Then ammonia was found, several structures of ammonia were found in G7929, again, one of the most puzzling objects. And then with the advent of ALMA, this field progressed a lot, and a circumstellar ring of carbon monoxide was discovered in Eta Car, in the waste of the homunculus. And now it's where our work comes into play. That's what I'm talking about in the next slides, the work that I did in my PhD thesis. So we started a campaign to detect a molecular gas around luminous blue variable stars. We built a sample of luminous blue variables, including candidate objects and also confirmed objects that displayed signs of eruptive mass loss. And we employed both single dish and interferometric observations to explore the molecular content of these objects. We use the IRAM 30-meter telescope, the APEX telescope in Chile, and of course, ALMA for interferometric observations. Also, we use the ARMA archive. And what did we find? Well, the first thing we found were a new type of molecular structure, new molecular rings around the sources MN101 and AG-CAR. Here you have the spatial distribution of carbon monoxide around these two stars, and you will notice these elliptical structures that seem to enclose the stars. Well, looking at the morphology, the relation between the gas and the stars seems quite obvious. Also, these structures have a very similar size. But there is an obvious question. What are these things? We interpret them as equatorial rings that are seen with a certain inclination. But in order to disclose their origin, we perform a depth analysis using radiative transfer modeling. And we found very interesting things. The first thing that we realized is that the two structures had very similar gas properties. The kinetic temperature of the gas varies from 10 to 100 Kelvin, which are warm temperatures, still cooler than the temperatures that you can find in other environments, like, for instance, protoplanetary disks, but still much warmer than the temperatures that you measure in a cold interstellar cloud. The densities were in that high of just 1,000 molecules per cubic centimeter, but the most interesting thing is the isotopic ratio. We use the 12CO to 13CO ratio as a proxy to measure the actual 12C to 13C ratio, and we measure values between 5 and 20. These values are much lower than the typical interstellar medium value of around 70 or 90. So this could be an indicator that this gas comes from the star, but we weren't so sure. But perhaps the most interesting thing about these structures is their kinematics. Here you can see the channel maps of carbon monoxide around the two stars, and you will notice that the spatial distribution of the emission as a function of the velocity is very similar. We see similar kinematic patterns that are compatible with an expansion movement. The problem is that these structures are very narrow in velocity. If you look at the channel maps, you see that the velocity extent is of less than 10 kilometers per second. And this would imply a very reduced expansion velocity. So in order to verify these kinematics, we built a three-dimensional models of the rings using the line radiative transfer code. And we tried to keep the models as simple as possible because at the end you have a lot of free parameters. So we use a simple axisymmetric density distribution with a power law, temperature law, and we try to reproduce the observed emission. And we managed to do so, especially with a model, the best fitting model of a slowly expanding equatorial ring with an expansion velocity of just 5 kilometers per second, which gives a dynamical timescale for these structures perfectly compatible with the luminous blue variable phase. However, this number is quite problematic because 5 kilometers per second is extremely low for an expansion velocity. To give you an idea, the typical expansion velocity of luminous blue variable nebulae is about 50 kilometers per second. So we are speaking of 1 order of magnitude less. So we realized that these structures were unusual. The next thing we did was to quantify their mass. So we estimated the mass of molecular gas from the CO observations using a standard conversion factor of 10 to the minus 4. And we found out that the gas around MN101 had 0.6 solar masses, and that the ring around AG-CAR was almost 3 solar masses. Okay, this is a good thing because these values are compatible with the mass ejection. We are not getting crazy numbers like 100 solar masses that would imply that these structures are just molecular clouds that happen to have a hole in the middle. But still, we are not able to see if this is really a lot of molecular gas. We need to put these numbers in context. And the best way to do so is to compare the mass of molecular gas to other circumstellar components. So we, again, exploit the synergistic observations at different wavelengths. So in the case of AG-CAR, the circumstellar nebula has 0.2 solar masses of dust and 6.6 solar masses of ionized gas. These are numbers that are comparable to the almost 3 solar masses that we get from molecular gas. And these numbers are very important and have strong implications because if this gas comes from stellar ejecta, which is something that is suggested by the chemistry, morphokinematic properties, and mass of the gas, this could imply that molecular gas is tracing at least a 30% of the total mass lost by AG-CAR. So it's a significant fraction of the total mass loss. As we will see later, this can have important implications for stellar evolution models. But we not only detected these two structures, we also had a look at another LBB object that is surrounded by a ring of molecules. If you remember the timeline that I showed before, there is a molecular ring in the waist of the homunculus. Just to recap, ETA-CAR suffered a great eruption in the 19th century, around the year 1840s. And this event was followed by a second, less energetic outburst that took place 50 years later, near the 1890, that produced what is called the inner ejecta, the little homunculus, which is a smaller structure that mimics the outer one, and the vagal blobs, which are small hot clamps of highly ionized ejecta that move very close to the orbital plane of the binary. So if you have a look at the waist of the homunculus with, let's say, molecular glasses, this is what you see. You see the ring of CO that was detected with ALMA, but we, analyzing ALMA archival observations, found a counterpart in other molecules, HCN and HCO+. This equatorial ring is the main molecular reservoir of molecular material in the homunculus, with a mass that, depending on the abundance that you assume, varies from 0.2 to 5 solar masses. And this ring is likely related to the great eruption that formed the homunculus. However, we also found what we call the inner molecular ejecta, two structures that seem to be linked to this second event that took place at the end of the 19th century. These are what we call hot bullets of HCN that are only detected in this molecule, and also a compact cloud of HCO+ that is possibly contaminated by adjacent emission from radio recombination lines. The important thing about these structures is that they are very, very close to the star, as demonstrated by the spectra. Here you can see the spectra of the HCN clamps seen in absorption against the stellar continuum. And as you can see, we also detect the vibrationally excited rotational transition of this molecule. And this indicates that the excitation conditions are very, very, very important, because this transition requires very high temperatures to be excited. So this proves that this material is actually very close to the star. So our explanation for all these molecules, as I said before, is that these were formed from stellar ejecta. We have several pieces of evidence that suggest this idea. First, that the molecular gas shows strong hints of extreme CNO processing, like, for instance, nitrogen-rich gas. We see a lot of nitrogen-bearing molecules, and also extremely low isotopic ratios, very close to unity, that are even lower than the ones that we measure in AG-CAR and MM101. And also the dynamical timescales of these structures seem to suggest that they were formed about the same time as the great eruption in the case of the ring, and also the lesser outbursts in the case of the inner ejecta. Please note that the ring of the main ring is expanding much faster than the rings that we observe in the other structures. So now let's have a look at this picture from Gould and collaborators 2020, who performed a spectral line survey using Herschel and discovered a lot of new molecules in different regions of the homunculus. The important thing about this object is that all this molecular blossoming took place in less than 200 years after the great eruption, so in very short time scales. This proves that these stars are able to sustain a complex molecular chemistry, even though they have strong conditions like strong UV fields, very hot temperatures. And this makes ETA-CAR a unique lab to learn about the formation and destruction of molecules in some of the most extreme environments in the universe. But there's a remaining question, a final remaining question. How are these molecular rings formed? What's the physical mechanism behind these rings? Well, the short answer is that we don't know yet, but we have some ideas on what mechanism can be responsible for the formation of the rings. The first is that the rings are remnants of binary interaction. For instance, a non-conservative mass transfer episode in a closed binary system that should produce a mass leakage through the outer Lagrange point, forming and expanding a structure. Or another possibility is a complete merger. And this hypothesis is supported by the fact that their recent models suggest that actually the great eruption of ETA-CAR was actually a merger in a triple system. Moreover, a recent paper suggests that AG-CAR can be a current binary. So definitely binarity seems to be playing a role in the shaping of all these structures. And another possibility is an equatorial mass loss event induced by fast rotation. We know that AG-CAR is a fast rotator. It rotates at a nearly breakup velocity in some parts of the S-door cycle. And also many other luminous blue variables are known to be fast rotators. So we could think of equatorial density enhancement due to this rotation that would produce a slower and denser wind in the equator, and therefore more suitable for the formation of molecules at low latitudes. But as I said, these are just some ideas that we have to explain these structures, and we need to verify them by observing other objects and also with modeling work. So just to recap, we surveyed 8 sources in the context of my PhD, and we got 5 confirmed detections of molecular material. The new slowly expanding structures in MN101 and AG-CAR, the fresh molecular ejecta that we found using ALMA archival observations in ETA-CAR, and also 2 other structures that I haven't shown because I have no time and are still work in progress, which are circumstellar shells of carbon monoxide around MM48, and a clumpy and complex molecular environment in AFGL 2298. So taken as a whole, these results prove that the formation and survival of molecular gas in the outskirts of luminous blue variables is more common than expected. Actually, molecular gas is a key ingredient of the circumstellar medium of these stars. But more importantly, in those cases where we can confidently link this molecular material to ejecta, we see that the molecular gas may represent a significant fraction of the total mass loss. And as I said before, this is important for stellar evolution models that are quite sensitive to this parameter, to the assumed mass loss rate. So it's possible that we are underestimating the mass loss, not only during the luminous blue variable phase, but in other post-main sequence stages. But let's have a look now at the family portrait of molecular structures around luminous blue variables. First, we have what we call large fragmented bubbles, which are molecular clouds that have been somehow disturbed by the stellar wind, but are just loosely related to the stars, as is in the case of G24 and G26. Then we have small scale structures like circumstellar shells in the case of G79 that are most likely material that has been compressed by the stellar wind. And on the other hand, we have the equatorial rings-like structures. At the beginning, we thought that the ring around ETA-CAR was an exception, but with the addition of these 2 new sources that are quite different, but not that much, we see that there might be a relation between all these structures. So what happens if we plot together the radius and the expansion velocity of the rings of AG-CAR, MN101, and ETA-CAR? Well, the thing that it's most obvious is that there is a 2 order of magnitude gap between these rings and this ring. But we can fill the gap by adding to the plot 2 other luminous blue variable-like objects that are surrounded by equatorial rings, which are HD 168,625, which is a candidate luminous blue variable, and SK-69202, which is the progenitor star of supernova 1987A. If we look at the points, there seems to be some sort of dynamical connection between all these structures. So it's reasonable to think that the rings of AG-CAR and MN101 are just older versions of the down ring of ETA-CAR. However, this is very speculative because we only have 5 points. We need to populate this graph with more points. But it's interesting to see that there are no objects falling in this region that would correspond to more energetic events, expanding faster and reaching a larger size in short timescales, nor in this region here that would correspond to events that took place in higher density environment and then get slowed down more quickly. So as I said, this is just a speculation, but it's an interesting and compelling idea to be explored. So what are the conclusions of this work? First, that molecular gas is a crucial ingredient in the circumstellar medium of luminous blue variable stars. Second, that if the gas comes from the star, may represent a 30% of the total mass loss or more. That star evolution models are quite sensitive to this parameter, to the mass loss rate. So it's possible that these results imply a revision of some star evolution models. But more importantly, that a rich molecular chemistry is possible in these stars, as proved in ETA-CAR, at least in very short time scales. And this is very important because it makes us to reframe the view of luminous blue variables and evolved massive stars in general as molecular polluters, and have important implications for the role of massive stars in the chemical enrichment of the early universe. So yeah, basically, we need to take into account molecular gas when we speak of massive stars. And how we can progress on this line of research? Well, the first thing is to extend the sample of molecular rings, looking for analog structures in other objects. Study the chemical complexity of these structures, for instance, looking for specific tracers of shocks or PDRs. Continue studying ETA-CAR, that, as I said before, is a unique laboratory to this kind of works. Understand the role of metallicity in the properties of these nebulae, for instance, looking for analog structures in extragalactic luminous blue variables. And finally, exploit the synergies with the continuum studies of star evolution possible thanks to the SKA precursors. And that's basically everything from my side. So if you have any questions, I would be pleased to answer them. Thank you so much.
Well, thanks a lot to you, Cristobal. This was a very nice and clear talk, very interesting. So let's see if we have any questions, either from here on Zoom. If you have a question, just raise your hand and I'll just call up your name. Or of course, people on YouTube, you can also ask questions. I'm going to keep an eye on that if I see any, but there's a slight time delay. So I see already here, Ashish has a question, so please go ahead and ask it.
Yeah. Hi, very nice talk. So if I understand correctly, the ring is expanding by 5 km per second, right? I was just wondering, what's the escape velocity at these scales?
That's a good question for which I don't have an answer right now, but it's something that we need to calculate. The thing is that, of course, this velocity is the current day velocity. Probably these events were expanding much faster in the beginning, because we're speaking of structures that are 0.2, 0.4 parsec in scale. So it's very large structures. So yeah, precisely this relation that we propose between the rings of these two objects and the ring of ETA-CAR suggests that in the beginning, all these events start by being very compact and expanding much faster. The expansion velocity of the ring of ETA-CAR is about 180 kilometers per second.
Okay, thanks.
For now, I see no other questions on YouTube, so I'm just going to take the chance and ask one. I was curious about the model that you said you made for these rings with your basically the ring shape. And I was wondering, I think you mentioned a bit about it, but I was more curious about why such a structure would be a ring shape and where the shape comes from. If you could say a few more words about that.
Yeah, sure. Of course, the starting point from this is the morphological interpretation we get from the CO maps. So we saw an ellipse. Seeing two ellipses with different elongations made us think that these structures are actually rings seen with a certain inclination. So of course, this is an oversimplification, because in astrophysics we want to work with simple models. So we started with these axisymmetric ring models. Of course, in reality, these structures are not homogeneous. They are very clumpy, and also there could be density gradients that produce different expansion velocities depending on the direction. But this is something that we need to incorporate in the models in the future, let's say.
All right, thanks. And if I may follow up, I still don't see a question on YouTube, so I think I can. Can you comment a bit more on binarity for these kind of stars? Because I think what struck me was the difference in shape between the nebula around ETA-CAR and then all the other ones that you showed that seem to be more like these shell structures, and then ETA-CAR has this very complex structure. It is a binary, it might have been a triple.
Yeah.
Are there more things known about the binary status of the ones that are these ring shapes?
Yeah, actually the topic of binarity in LDBs is a quite complex topic, because it's not easy to find companions for this star, because they are so bright and they the lines are very broad. These are variable, so it's a mess, let's say. Actually, until very recently, I think there were only 3 luminous blue variables that were known to be current day binaries: ETA-CAR, HR-CAR, and I don't remember the other. But the thing is that no, a couple of months, no, but some months ago, a paper was published with BLT observations that reported companions for 8 or 9 additional luminous blue variables. So it seems that luminous blue variables follow the general trend of massive stars of being binaries. And an indicator of this is that most luminous blue variable nebulae show some sort of bipolarity. They deviate from spherical symmetry. So that's an indicator that binarity is playing for sure a role in this kind of structures.
That's very interesting. Thanks a lot. I think it's time to hand over to the second part of our Hypatia Colloquium. So thanks again, Cristobal, and I will hand over to our second chair, Ashish, for today.
Thank you, Julia, and thank you, Cristobal, for the very nice talk. So our next speaker is Linda Lombardo. She is a PhD student at Observatoire de Paris in France, and she will present her research titled A Close Look at Young Intermediate Mass Giant Stars, Clues of Rotation and Mixing. So Linda, the floor is yours. Yeah.
Thank you very much. I'm sharing my screen. Okay. I hope you see it and you hear me well. Okay. So before starting, I would like to thank the organizers for giving me the opportunity to speak today. And in today's talk, I will present you the results we have obtained for the chemical analysis of a sample of young massive giant stars that we serendipitously discovered. Sorry, okay. Before going into the details of the chemical analysis, I would like to explain to you how we discovered the stars. Our original goal was to determine the chemical abundances, and in particular, the abundances of neutron capture elements in a larger sample of giant stars, with metallicities between -2.5 and -1.5. The abundances of neutron capture elements are particularly important because they allow us to understand the physics of the neutron capture processes, as well as the chemical evolution of the galaxy. And this intermediate metallicity range is particularly important because it allows us, as you can see from the figure, to distinguish between the different formation scenarios for neutron capture elements. So for the target selection, we relied on the Strömgren photometry from the Paunsen catalog, combined with the Casagrande metallicity calibration for giants, in order to select the targets with the desired metallicity range. So once we have selected the targets, we observe the stars with different facilities in order to obtain high resolution and high signal-to-noise ratio spectra. But when we first analyzed this spectra, we immediately realized that something has gone wrong because we, as you can see from the figure on the right, these stars appear to rotate, and also some of them rotate quite rapidly. Usually when we are studying all the metal-poor giant stars, we don't expect them to rotate so much. So it means that these stars are not old and metal-poor, but in fact they are young and at solar metallicity. But what has gone wrong with our target selection? Well, the reason can be seen from the column magnitude diagram here on the right. As you can see, our stars are in a region of the column magnitude diagram where all the metal-poor isochrones, so the gray one, overlap with the young solar metallicity isochrones. And this effect is called the age metallicity degeneracy. So this means that in our case, the photometric metallicity calibration has been affected by this degeneracy. So instead of observing all the metal-poor stars, we found these young solar metallicity stars. So we had a sample of 26 giant stars with the solar metallicity. And from the evolutionary tracks, we deduced that these stars must be very young, with ages between 0.1 and 1 gigayear, and also quite massive, so with masses between 2.5 and 6 solar masses. These high solar masses suggest that these stars were from A to B type when they were on the main sequence, and now they are evolving to the red giant branch. These stars, however, are very interesting and also poorly studied, because the time spent by stars in this evolutionary stage is quite short compared, for example, to the main sequence or the red giant branch. Also, by studying these stars, we can have information on the evolution of post-main sequence stellar rotation, as well as information on stellar mixing due to rotation. We derived the stellar parameters for these stars using the Gaia EDR3 photometry and parallaxes. In particular, the effective temperatures were derived from the Mucciarelli et al. 2021 color temperature calibration for giants, while the surface gravities were derived from the Stefan Boltzmann equations written here. And finally, the microturbulent velocities were estimated using the Dutra Ferreira et al. 2016 calibration. We derived the metallicities for the stars, so the iron abundance, by measuring the equivalent weights of the line. For the most rotating stars, in particular for stars that have a rotation above 15 kilometers per second, in measuring the equivalent weight, we take into account both the Gaussian and the rotational profile of the line. I put this warning because when we are dealing with rotating stars, of course, the stellar rotation affects the line broadening. So when we are measuring the equivalent weights in such rotating stars, the stellar rotation allows us to detect only the strongest line. So we have to be careful in selecting the lines that are not so saturated. We were able also to measure chemical abundances for several elements, in particular from oxygen, magnesium, aluminum, and calcium, by measuring the equivalent weight of the lines, and for other elements from carbon to europium, using the spectrum synthesis technique. Here I put a reminder just to remind what I mean for chemical abundance. For a certain element X, the abundance is defined as the logarithm of the number density of the element X above the number density of hydrogen plus the 12. And for this notation, I mean the abundance, the difference between the abundance of the certain element for the star minus the abundance of the same element in the sun. This other notation is what I mean for abundance ratio. And it's simply the difference between the abundance of a certain element X minus the abundance of iron in the star. We were able to measure the rotational velocities in these stars by performing a chi-square minimization fit on the observed line profile, using different synthetic spectra with different rotational velocities. In this way, we derived that the vis and I of our stars were between 4 and 27 kilometers per second. We also checked for potentially binary stars in our sample, because we have found that 2 stars in our sample are in the Washington double star catalog. So we looked for hints of potentially binary stars by looking at the Gaia DR2 radial velocities of our stars. In particular, we looked for the stars that had Gaia radial velocities errors above 1 kilometer per second, which is the typical error that we can obtain for the stars of this magnitude. We also checked for stars that had Gaia radial velocities that differ of about 5 sigma from our observed radial velocities. And finally, we looked for stars that are in Kervell et al. 2019, and the stars were identified as probable binary stars from proper motion anomalies. In this way, we obtained that 2 stars in our sample present all the above-mentioned characteristics, and they are likely binary stars. We wanted to compare our results with the one we have found in literature. As I said before, the stars are poorly studied. So we have found in literature only A-type stars in the main sequence, or FGK dwarfs, or FGK dwarfs. So we don't have a true comparison with the same type. However, for the like elements, we can see that the abundance of carbon for the majority of our stars seems to be lower than the solar value, and for the majority of our stars, the nitrogen abundance is overabundant or is over solar, which means that this underabundance in carbon and overabundance in nitrogen means that the material in the photosphere of our stars is mixed with the products of the CNO cycle that burns hydrogen. This hypothesis is supported by the C plus N plus O abundance ratio, which is almost solar for the majority of the stars. For the light elements, we have found a good agreement with the previous studies in general, except for these two stars that present, one of them, an abundance of aluminium over iron that is higher than the majority of the stars in our sample, and another star that have a calcium over iron below, very low respect to the other stars in the sample. However, as I said before, the stellar rotation can affect our measurements of the equivalent weights, and these two stars appear to rotate quite rapidly. And you can see that this implies a very large uncertainty on the chemical abundance. From the point of view of the neutron capture elements, we have found that our results are in line with the one found in literature for other A-type or F and J dwarfs. But as you can see, for the majority of our stars present neutron capture elements that are almost solar, with the only exception of the barium abundance. As we can see from the figure, the majority of our stars present a barium enhancement and, of course, solar and capture elements. We usually don't expect these results in these stars, because for the barium enhancement and also the neutron capture processes enhancement, the neutron capture elements enhancement are expected in AGB stars and not in subgiant stars. So what can be the cause for this barium enhancement? We first check for non-local thermodynamical equilibrium effects, and we checked for the non-LT corrections for barium lines provided by Corotin, but the corrections decreases the barium abundance by 0.1 dex, which is of course not sufficient to match the solar value. Another possibility could be that we underestimated the microturbulent velocity in our stars. And we can see that for this star, HT 55077, an increase in macroturbulence of 0.6 kilometer per second decreases the barium abundance by 0.6 dex. However, we don't have any observations that supports such a high macroturbulence that would of course affect not only the barium abundance, but the abundance of all the elements. Another possibility could be that our stars may be mild barium stars. Barium stars are a peculiar type of subgiant stars that present a strong barium enhancement and also an enhancement in other S process elements. Mild barium stars are a subcategory of barium stars that show the same enhancement but less prominent. To check this hypothesis, we compared our stars to the one in De Castro et al. 2016. In this figure, you can see that the green squares are the stars that were identified as barium stars in the Castro sample, while the black squares are the stars that are considered to be normal. This difference is due to the S over iron abundance ratio, where S is the sum, S over iron is the sum of these S capture elements, abundance ratios, and the difference between, and the discriminant between these two categories is the value of 0.25 dex. As you can see, the majority of the stars in our sample present an S over iron below this value, except for these 3 stars. So it's possible that for the 3 stars that have a value above 0.25 dex, these stars may be, in fact, mild barium stars. But for the majority of the stars in our sample, this explanation cannot stand. So we don't have a clear explanation on why we have found this barium enhancement. We wanted also to compare our measured rotational velocities and chemical abundances with the one predicted by stellar models with rotation, and in particular the one by Gheorghi et al. 2013 at solar metallicity. In this plot, I'm showing the values predicted for the rotational velocities of the stars with different values of omega, where omega is the ratio between the initial angular velocity and the critical angular velocity. Of course, this comparison is not completely correct because the models predict the actual rotational velocity of the stars, while we were also only able to measure the vicinity, which depends on the inclination angle of the stars along the line of sight. So, however, we can consider the vicinity as a lower limit of the actual rotational velocity of the star. And in this way, we have found that our measured vicinity are compatible with the rotational velocities predicted by models with omega between 0.3 and 0.6 dex. We wanted also to compare our nitrogen over carbon abundance ratio with the one predicted by models. And as you can see from the figure, our values seems to be consistent with the value predicted for clump stars. The clump is the region of the column magnitude diagram where the stars are located when they undergo central helium burning. So it's true that our stars are warmer than the maximum extent of the clump, but their chemistry seems to be compatible with the one predicted by the clump, for the clump. So since the clump phase is much longer than the subgiant phase, we think that it's highly probable that these stars are in fact clump stars and not subgiants. Okay, here is a summary of the main conclusion we have obtained in this study. The first important thing is that the photometric metallicity calibration are affected by the age metallicity degeneracy. So when we are using these calibrations, we have to keep in mind that we can be affected by this effect. The sample of stars we have analyzed have masses between 2.5 and 6 solar masses. That suggests that the sample is composed of evolved A to B type stars. And this hypothesis is also supported by the chemistry, which is similar to the A to B type stars in other studies. The low carbon and the high nitrogen abundance ratio suggests that these stars have undergone mixing, and this is in line with the prediction of stellar evolution models for clump stars. And we have also found that our measured VSNI agree with the theoretical values predicted by models. And finally, that the majority of the stars in our sample present barium enhancement, but low S over iron ratio, which makes them similar to mild barium stars, but is not sufficient to explain this enhancement. And that's all. thank you for your attention. And if you have a question, please tell me.
Thank you, Linda, for the very nice talk. So any questions? If there are no questions yet, maybe I can ask something. So I think this is very interesting that you found this barium enhancement. So what kind of future follow-up can you do to like distinguish among the possible reasons for this enhancement of barium?
Well, the point is that this barium enhancement has been found in several studies, and we are trying to interpret this, but in fact, nobody has really found the real explanation, because it's something that you don't expect. For example, for barium stars, you have this, I forgot to mention that barium stars present these peculiarities because of the mass transfer with an AGB companion. So they present these peculiarities for this reason. So it's difficult because there are, in other studies, they also have taken into account the effect of a magnetic field, but it seems not sufficient to explain this. So it's quite difficult to explain this.
Okay, thanks. So any questions? Okay, maybe I can ask one more. So I think initially you told that the surprising thing was that these stars are rotating very fast. So probably they are the metallicity is like has to do something with the rotation. So like, why is that? Sorry, I'm not at all familiar with this field, but what's the relation between metallicity and rotation speed?
Well, in fact, it's because they are young. So when the star is on the main sequence, it rotates rapidly. And when they evolve to the red giant branch for the old metal-poor stars in the RGB, their expansion makes them slow down. That's essentially why they are not rotating. And when we have found that these stars were rotating, they can rotate also, or because they are rotating and they have this rotation, residual rotation from the main sequence, or because they are in binary systems. So this is why it is not correlated with the metallicity, but for this thing.
Okay, thanks. So I think Julia has a question. Julia, please go ahead.
Well, thanks. Yeah, thanks for the interesting talk. I also have a question, actually, with respect to both of the things you just mentioned. So as far as I know, or as you just said, the barium stars are basically the mass gainers in previous binary interactions. So they often have, for example, white dwarf companions because their companions have evolved. And I was wondering if that could be the case in your systems as well, and what is known about their binary status.
Well, in fact, there was something interesting, and I was discussing this in this slide. We have tried to find some companions, and in fact, we don't have enough information about their status if they are in binary systems. And maybe it's possible that some of them are in fact in a binary system with a white dwarf. But I think this would be something that we will discover when the Gaia DR3 will come out, and we will check if they have a companion. But for now, we just check for variations in the radial velocities or proper motion anomalies. We had this hint for these two stars, and these two that were in the double star catalog, Washington double star catalog. One is actually in a binary system, this one, because the parallax are consistent. But the other one is only a visual double system. The parallaxes are completely different. But yeah, it's something that probably we're going to find out when the Gaia DR3 will arrive.
Well, sounds interesting. We're going to wait for that then.
Okay, I guess if we don't have any more questions, we can end the colloquium today. So any comments? Okay, thank you to Paula.
Yeah, Linda, thank you a lot. You can eventually stop sharing. And it would be nice to see you and Cristobal for a while, just to wish you all the best for your future career. It was very interesting and quite important to host you here. I hope that this will help you and make you visible for your important work. Thank you to Julia and to Ashish for chairing this session, and I wish you all the best, and see you next week when we have 2 other speakers. So have a nice day, evening, or night. Bye.
Thank you very much.
Bye-bye. Thank you.
Bye.
Thank you. Bye-bye.